Okay, let's start. In this lecture, we will first continue with permutation or multisets. And first, we give a combinatorial interpretation of the previous result. So look at the following theorem. Actually, the theorem is already proved, but we just give a different interpretation. So let M be a summation of n1 to nk, and each ni is greater than 1, greater than or equal to 1, and then the number of ways to partition a set of n objects into k labeled boxes in which box 1 contains n1 objects, box 2 contains n2 objects, and blah blah. Box K contains nk objects. So the number of the partition and the following rules and the rules equals n factorial divided by n1 factorial times n2 factorial times all the way to nk factorial. This is a result we already proved before, and this is a general case, and for a special and slightly different case, if boxes are not labeled, that means you cannot distinguish box 1 from box 2, and n1 equals n2 equals all the way to nk, then the number of partitions equals n factorial divided by k factorial n1 factorial times nk factorial. So notice that here you have extra factor k factorial in the denominator. This is because for each partition in the first case, in the red star case, then for example, a remark. Let's do a small remark. Box 1, box 2, box K, and here you assume you have A1, AN1, let's see, B1, BN1, C1, CN1. Okay, so this is a partition in the first case, but when you suppose you have another partition which is different in the sense of the first case, but now if you consider the second case, since the boxes are not labeled, so you cannot distinguish the first one from the second one, they all map to some kind of configuration. In the sense of the second case, as soon as you have A1, AN1 together, B1, BN1 together, C1, CN1 together, which is contained in the first box is not important. So totally on the left-hand side, you have K factorial rearrangement of the boxes, which all map to the same configuration in the sense of the second case. So that's a reason why we have an actual K factorial in the denominator in the second case. Okay, now let's look at a slightly complicated example. So suppose M is a multiset with elements 5 times X, 2 times Y, 8 times Z. Then what is number of all 13 permutations? Solution. Since totally you have 15 elements, okay, therefore to find 13 permutations, we first try to fix the elements included in that permutation. Or in other words, we try to drop 2 elements. So suppose we are missing X and X, then the 13 elements will be the same as 13 permutations will be the permutation of 3x, 2y, 8z. And if you missed x and y, then certain permutations in this case will be just a permutation of 4x, y, 8 times z. And then similarly, you have the case missing xz, missing yy, miss yz, zz, and the permutations of this is 4x, 2y, 7z, 5x, 8z, 5x, y, 7z, 5x, 2y, 6z. Okay, now what is the number of permutations in each case? So for the first one, you have (13 factorial divided by 3 factorial. You just use the previous result, 2 factorial, 8 factorial, and then you have 13 divided by 4, 1, 8, 13 factorial, 4 factorial, 2 factorial, 7 factorial, 13, 5 factorial, 8 factorial, 13, 5, 1, 7 factorial, 13, 5 factorial times 2 factorial times 6 factorial. Okay, and the number. So the number of all 13 permutations of the original set M will be just a summation of all such numbers of permutations of subsets. Okay, and a small remark is if we change 13 to some other numbers, the situation will be slightly different. But the strategy is the same. First, you choose the number which included in the permutation, and then use treat the K permutation as a full permutation of some subset. Okay. For example, if let's think about K permutations, 7 permutations, then the problem will be quite difficult, because no matter how you choose, either dropping 8 elements or choose 7 elements, then it's very hard to actually enumerate all the cases. So in that case, it's better to use computer or do some coding. So all I want to say is the idea is simple, but in reality, usually you cannot just use the idea and work by hand. Most of the time, you need to turn to computer for help. But with the basic idea in your head, you can largely simplify the work of computer. So remark, we always turn to computer in the end. In reality, but different strategy gives totally different turn back. It receives. Turn back from computer. That's why people study the applied math or computational math. And so in one word, if the word is no speciality at all, then as the number goes up, you cannot do any computation. We can only solve the computational problem for special cases. Why? Because they are special. They have some speciality. They have some key features. If you capture that key feature, you can largely simplify your computation. So all we human need to do is find out their key features. Okay, so that's also one of the purpose of this course, give you some feeling how to capture their features or key features, or how to understand something is understandable, something is not, so far. Okay, next let's look at some applications. So how many ways we can place 3 mutually non-attacking rocks on a 3x3 chessboard. But this is easy, and we can just draw the picture by hand. In combinatorics, it's also very important that you can enumerate for the small numbers. That's how you find the patterns. So first, let's choose the rook on the 1-1 position and 2-2 position, 3-3 position. This is the first configuration, and then you keep the first one and change the second one. Since you choose first one, the second one can only be chosen from 2-2 position to 3-3-2, 3-3 position. And then we choose this one. And then the last one must be here. Okay, then it's easy to verify. If you fix the first roof, then these two configurations are the only possibilities. Now, if you change R to this position, then similarly, you can have two configurations. Finally, you have other two configurations as this. Okay, now, so the total number is 6. Okay, next we generalize the above case to arbitrary size, the chessboard with arbitrary size, n by n chessboard, and n mutually no attacking rooks. And similarly, the idea is no matter how you choose, we can write down the coordinates for each rook. And the first coordinates, let's see, is the first row, and the second coordinates means the number of columns, and 2, I2, N, I, N. And since they are not attacking each other, therefore I1 to IN is a permutation of 1 to n. So for this, we can verify it for the above 6 configurations when n is 3. So for first picture, the first rooks has coordinates 1, 1. Second one is 2, 2. Third is 3, 3. So I1, I2, I3 is 1, 2, 3. And for the second picture, you have 1, 1, 2, 3, and 3, 2. This is 2, 3. This is 3, 2. Therefore, the permutation is 1, 3, 2. And for second one is 1, 2, and 2, 1, 3, 3. So it's 2, 1, 3. And then you have 1, 3, 2, 1, 3, 2, 3, 1, 2. 1, 2, 2, 3, 3, 1, 2, 3, 1. 1, 3, 2, 2, 3, 1. So the permutation is 3, 2, 1. And then if you look at those permutations, 1, 2, 3, 1, 3, 2, 2, 1, 3, 3, 2, 1, 2, 3, 1, 3, 2, 1. They are just permutations of 1, 2, 3. Okay. So that's how you understand this statement. As soon as you accept this, then the number of ways to put non-attacking rooks will be n factorial. Okay, and next example, let's do slightly variation. Suppose you have n color, n distinct. Suppose you have n rooks with distinct colors, and then how many ways to place them into n by n chessboard in non-attacking way. Okay, so the way we solve the problem is we decompose the whole procedure into 2 steps. So first step, step 1, we just put n rooks into non-attacking position. So we get the configurations without color. So totally you have n factorial ways because of the last example. And second two, let's color the configurations. So suppose you have a chessboard, n by n chessboard with n non-attacking rooks on it. So let's see. Okay, let's do this. Okay, for example, like this. And now let's color these rooks. So how do we color it? Because each row and each column, you only have one rooks. So how to color? choose a color for each row or each column. And as soon as the rook is on that row, you just color it in by the same color. Okay, then for example, you can choose red for the first row. So for first row, and purple for the second row, and green for the third row, and yellow. Okay, then no matter how you what configuration you have in the first step and the ways in the second step is n factorial. Let's see. Okay, so totally you have n factorial times n factorial ways in this case. And a slightly more complicated problem is, suppose n is n1 plus n2 plus all the way to nk, and you have n1 red color rooks, n2 green color rooks, nk, for example, purple color rooks, and how many ways to put them in non-attacking positions. And noted that here, if the rooks has the same color, we cannot tell which one is which. So they are indistinguishable. They are identical. So we still decompose the problem into two steps. Step 1 is the configuration and the same. And step 2, and if you remember this, then what we are going to do is color n columns or rows such that n1 columns are red, n2 columns are green, nk columns are purple. So that's a problem of permutation of multisets. So totally you have n factorial divided by n1 factorial, n2 factorial, all the way to nk factorial. Okay, therefore totally you have n factorial times n factorial divided by n1 factorial, n2 factorial times nk factorial. Okay, so as a simple conclusion for this section, you should be sensitive to this formula. When do you have this formula? And when you do exercise, please really try to understand the phenomena and don't try to use formula directly, because so far you only know very little formulas, not so many formulas, so you can actually guess which one is which without totally understanding it. But later on, when you have more and more formulas, you will get confused if you don't have a true understanding. Okay, next, as you can guess, if we can define permutations or multisets, then of course we can define the combinations of multisets. And so that's the definition. Let M be a multiset for K between 0 and the cardinality of M. A K combination of M is an unordered selection of K elements of M. And remark, we haven't defined what is a subset of multiset, but if you define a subset of a multiset, then a K combination of M is a subset, for example, MK, such that the cardinality of MK, subset MK of M, such that the cardinality of MK is M. We will not use the second definition, but I'm just saying, if you would like, you can get a different definition. So in mathematics, actually, there's no common definition. By this, I mean, when you deal with a real problem by yourself, you can do your own definition as soon as they are consistent with each other and with knowledge you know. Just like I also define something in my own paper because they're not defined by other people's before, so I have the freedom to call it by whatever I want. So that's also the case for you. Later on, if you find something new and want to introduce some convenience definition for yourself, then go ahead. All rules are to be broken. Okay. Now let's look at some examples. Suppose M is a multiset 2A, 1B, 1C, and then two combinations. So you choose two elements. So then you have 2A, AB, AC, BC, and of course one combination is just ABC, and then okay, for convenience let's write down it. One combinations A, B, C, and 0 combinations, just empty set. And now let's look at the following theorem. Suppose you have multiset. So as soon as we define what is the combinations of multiset, a natural question following is how many ways, so how many combinations do you have? And the case is also very complicated, but for some special cases, we get a perfect answer. Suppose our multiset S is infinity times 1, infinity times 2, infinity times K. then the number of R combinations of S is R plus K minus 1. Choose R. Or by the formula before, it's R plus K minus 1, K minus 1. This is because we know before n choose K is n choose n minus K. Okay, and I should mention that this is very important theorem so far, and the proof also gives you some general idea how we carry out strategies in combinatorics. We always transform a problem into a simpler one, and finally to a model we already know. And in the intermediate process, usually we drop off all the real meaning of the problem. We only capture the mathematical meaning. Without dropping the real meanings, you cannot go too further. Cannot go too far. So that's a strength of the abstractions. Just like philosophy. Why we study philosophy? Because philosophy comes from life, but not focus on some specific things. They tell about the general principle in the world. And if you can apply them, they are useful. Okay, now, so suppose you have chosen x1 ones, x2 twos, xk k's. That means you have 1 1 1 x1 2 2 x2 k 2 k xk. And the problem for a k combination of S is the same as the following one. The summation of x1 to xk is R, and x1, x2, xk are non-negative integers. And it is clear that integer solutions of star x1, x2, xk is 1-to-1 corresponding to R combinations of S. So that's a very important abstraction. That means the real problem we can forget about. It's not anymore a K combination problem. So the problem is that what is the number of integer solutions, non-negative integer solutions of of the following indeterminate equation, linear equation. So noted that if usually we have a linear equation, and if we have 3 variables, we need 3 equations to determine a solution. Without knowing that, you have infinite many solutions. But now we want integer solutions. Okay, so and the non-negative condition, you only have finite many solutions instead of infinite many solutions. So that's a slightly different, a different way in combinatorics, the discrete world and the continuous world in calculus. In discrete world, usually we consider those indeterminate equations. That means you have many solutions, and our purpose is just to find out a number of solutions. In real world, usually your problem should have only one solution. Otherwise, it's not well defined. Okay, so probably you need to change your mind in a slightly different way from calculus, linear algebra to combinatorics. And we don't know how to solve it, to be honest. But whenever you don't know how to solve a problem, just think about, can you solve a simpler but a similar problem? So here we have a simpler one, or similar one. We call a similar question. Just accept that most of people are not genius. We are clever, but not genius. So we mimic similar problems and to work out new ones. So you cannot build a world from empty. You always build your own work upon other people's work. So although we don't know how to solve the previous one, but if you had the following one, it seems like you have a way to go through it. So the question is the number of integer solutions. O delta, O triangle. Okay, and now let zi be y1 plus y2 plus all the way to yi for I from 1 to k minus 1. Then you have y1 is z1, y2 is z2 minus z1, yk minus 1 is zk minus 1 minus zk minus 2. Yk is r plus k minus zk minus 1. And then the equation, the problem delta, can be transformed to a new one called, for example, square. So in square, what is the problem? You have 1 less than z1 less than z2 less than all the way to zk minus 1 less than r plus k. So in other words, each integer solution y1 to yk, 1-to-1 corresponding to such increasing sequence of z1 to zk plus 1. Okay, then what is number of such sequences according to the problem delta? That is, choose k minus 1 elements from 1 to all the way to r plus k minus 1. And then the total number, just r plus k minus 1. Choose k minus 1. Therefore, there are r plus k minus 1, choose k minus 1 integer solutions of delta, the equation delta. Okay, now let's turn back to the original problem. Star. So if you compare the difference between star and triangle, you'll find the only difference is for x case, we require x to be non-negative integers. And for the second case, delta case, we require we require y to be positive integers. So let yi to be xi plus 1, 1 less than k. Then each solution of star one-to-one corresponding to a solution of delta, and therefore the number of solutions of star is r plus k minus 1, choose k minus 1. Okay, so that's how we prove this. And from the proof, I should say the most important one is this step. You just transform an equation into a number picking problem. So recall that in the square situation, you don't have equations at all because you already solved them. So the only requirement is your sequence is increasing. Okay, in your textbook, you have a slightly different interpretation for the proof, but the idea is the same. They just put cutting into positions and view the cutting the same way as a position. Therefore, you have r plus k minus 1 positions, and then choose k minus 1 cutting. The reason I introduce a slightly different proof is because, from my point of view, it's easy to remember the mathematical way than every time you put in some cutting into some positions. Okay, so that's the proof. And in general, if you don't have infinitely many ones, in other words, if S is n1 times a1, n2 times a2, nk times nk, and then you will have a problem. x1 plus x2 plus all the way to xk equals r, and then the restriction on x1, x2 will be two sides. That is, you have upper bounds for x1. Recall that if n1, n2, nk are infinity, then you don't have upper bound. You only require they are non-negative. Okay, so the equation you have is like this. And what is the numbers of non-negative integer solutions? Is a number of non-negative integer solutions. Okay, so this will be a very difficult problem. It's similar to some problem in number theorem, differential equation, or whatever. Remark. If R is strictly or not strictly is less than or equal to n1 to nk, then it is same as infinity case. If you are lucky enough, R is quite small comparing to n1 and to nk, then actually you don't have any restriction at all. In general, it is difficult to obtain a closed formula. Okay, next we talk about finite probability. It's also called a classical probability. That means, what is the difference between classical probability and modern probability? Is that the difference is that for classical probability, you're always counting finite number events, and your probability just point-wise. For each event, you have some fraction, okay, and the summation is 1. But for the modern probability, usually you have measure, you have a integrable function. So what you are really doing is real analysis. Okay, you need to use the Lebesgue-Dominic theorem, you need to use the convergence, all kinds of convergence, point-wise, almost everywhere convergence, L1 convergence, weak convergence, whatever. Okay. So if you are interested enough, you can choose probability course. That's very interesting. But also it relates to the stocks and some time series, martingales, or whatever. But in this course, we talk about finite probability. Actually, in physics, probably there are no strong distinction between finite and the modern one, because you can always discretize them. You just view them as a Dirac measure. Okay, so I will not talk about too much about the other things. Just focus on the on its connection to combinatorics. So there is, but setting will be similar. There's an experiment, Kyle E, which, when carried out, results in one of a finite set of outcomes. Assume that each outcome is equally likely, or you can call such an experiment randomly. And the set of all possible outcome is called the sample space of the experiment, and is denoted by S. Then S is a finite set Sn, and when n is carried out, each Si has a 1 over m chance of occurring, and therefore we say probability of Si is 1 over n for I from 1 to n. Or sometimes you just write the probability as PRSI. And an event is a subset E or S, and then the probability of E is defined to be, in our case, is cardinality of E divided by M, or in general case is defined by summation of all of the probability of all elements in E. Okay, now let's look at some example. Actually here for random, although in mathematics you can state it quite simply, you just call them random and assume that each outcome is quietly equal. But in reality, they have quite different meaning. I will explain my understanding of it, but it depends on you how to understand it. It's not a common rule. Okay. So let's consider the experiment. Kyle E of tossing 3 coins. For each one, you have head and tail, 2 cases. So after 3 times, you have head, 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 tail, head, tail, head. Head, tail, tail, and then tail, head, head, tail, head, tail, 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 head, tail, tail, tail. Actually, you already have the idea how many different outcomes you have in total. It's just 2 to the third power, so it's 8. And let's consider an event E. Suppose at least 2 heads up. Then the subset E is HHH, HHT, HTH, THH. And if none is treating, then HHH blah 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 TTT have the same chance of occurring, so that the probability is 1/8. Probability for occurring HHH is 1/8. It's under condition none is treating, but if someone is treating, then the answer is different. You cannot assume they are equal likely. You need to do experiment and get if someone is cheating, you need to do experiment to get the probability. Of each outcome. This is by the large number theorem. So as soon as you have enough experiments, and the total probability will be close to the actual probability. This is a very complicated problem. It involves the philosophy of how we understand probability. What is the hell is a probability? Actually, probability is always idealization, but how we understand it is also a big problem. Okay, I will not talk about this. Okay, now let's look at a different situation. Suppose you have 2 identical bosons. So recall that for 2 identical bosons, you cannot tell which is which. And suppose each has 2 states, so either 0 or 1. This is just a simplification. Probably you will have many states, but let's assume you have 2 states. Then what is the outcomes? Quite different to the tossing coins experiment. Now you don't have 4 outcomes. You only have 3. That is 0, 0, 1, 1, and 1/√2. 0, 1, plus 1, 0. And each has probability 1/3. When I first learned this, it's quite astonishing in physics, because it seems to me they are so similar to the tossing coin model, but actually they're not. The reason is that, we say something appears equally likely if we don't have reasons why they don't. That means if we have some reasons they are not equally likely, then we need to take that into consideration. Just like the bosons case, if you have two identical bosons, then obviously you have solid reason. They are not equally likely. I mean 0 0 0 0 1 0 0 1 0 1 1 0 1 1. This is not valid anymore. Okay, then you have three cases, but for these three cases you don't have a solid reason. If the first 0 0 occurs much more frequently than the second one 1 1. If you don't have a solid reason, then you just view them as equally likely. This is also the same for the case tossing coins. So if you are not sure someone is cheating, then they have the equal chance of occurring. But if you are sure someone is cheating and you can figure out how to compute them, then you can take that into consideration. Otherwise, you need to do experiment to actually test it. It's quite likely that, for example, if the first one, if you have three people and each one make a coin, and then they toss them together, although each one may cheating, but final result might still be equal likely for some events. Okay. Yeah, I will not talk about that too much. Okay, so now suppose you have ordinary deck of 52 cards, and you have 13 ranks, 1 to all the way to 13. 1 you can also view as A, so it's after 13 or before 2. And the 4 suits, cups, diamonds, hearts, spades, and the experiment Kyle E. Drawing a card at random. So E is an event that a card drawing is 5. Then you can write down in this way: E is a set consisting of 4 elements: C5, D5, H5, S5. And now if you look at the example as following. So first, we call 5 cards full house if 3 cards of 1 rank and the other 2 cards of a different rank. Okay, then of course you want to know what is the probability of occurring a full house. So let S to be set of all 5 cards, and then the cardinality or S is 52, choose 5. And E is event of 4 house. That means you have 5 cards which have 3 cards of rank 1 rank, and 2 other have different rank. Okay, now we need to estimate what is the cardinality of set E. And we compute it in several steps. So step 1, we choose the rank of 3 cards. Then, and step 2, and choose suits for these 3 cards. Step 3, choose rank of the other 2 cards. And step 4, choose suits for the other 2 cards. And in the step 1, you have 13 ways to choose rank 1 to 13. You can choose whatever you want. And when you choose a suit, you have 4, choose 3. And then when you choose rank for 2 cards, you only have 12 choices because you already chose one. And for the suits, you have 4, choose 2. Therefore, the cardinality of E is 13 times 4 times 12 times 6. And then the probability of E is cardinality of E divided by cardinality of S, and blah blah. Okay, and similar problem. So let E be the event that poker hand, that means 5 cards, contains at least 1 ace. Okay, then to compute it, we use the complement principle. Suppose we take the complement of the event. So the event EC is poker hands with no ace. And then the cardinality of the set EC is 48, choose 5. And then the probability of E is cardinality of S minus cardinality of EC divided by cardinality of S. And the remark is the question will be slightly different, more difficult than it. So let E be an event the poker hand has at least 2 aces. So how to solve this problem? Okay, I will not continue this. And you might have quite similar problems asking for what is the probability of the event E, which is defined by contains exactly 2 pairs. Okay, and blah blah. You can find it in your textbook. And a similar problem will be now. So I will not talk about the poker problem again. And for dices, this is another kind of problem. So suppose 3 dice are rolled, and you want to know what is the probability when the summation is 8. Okay, so of course the total outcome is 6 to 2/3, and the event E XYZ is 1 less than X less than X, Y Z less than 6, X plus Y plus Z equals 8. Okay, and now the cardinality of E is 7/2, because that is just the case when R is less than or equal to the upper bound for XYZ, not XYZ, for the variables. And you can transform to X1, X2 less than 5 greater than 0. And the summation is 5. And this is the case R less than the upper bounds. Okay. Now, so you have this formula, and then the probability is 7 choose 2 divided by 6Q. And a more difficult problem is if E is the event's summation is, for example, 6, then the problem is more difficult because R is no longer greater than the upper bound. Then you cannot use that formula. Okay, so I leave this problem to you. Okay, I think we don't have time to talk too much about the birthday paradox, but you can search on Wikipedia. So suppose we have 50 people, and then 2 people had the same birthday. And then the probability is, I can't remember, is so E is 2 people have the probability. So the probability of E is almost as like 0.97. If we have 100 people, just like in our class, then we have very high probability that 2 of you have the same birthday. You can congratulations at the same time. Have birthday party. Okay, I will stop here. Next time we will talk about pigeonhole principle.